This is Click Future. Welcome back to a series on Tech Convergence, where we explore the fascinating intersections of today's most revolutionary technologies. In our previous episodes, we've explored sentient machines, the quantum internet, brain-computer interfaces, digital twins, the new space race, fusion energy, quantum biology, and quantum machine learning. Today, we're venturing into the solar system to examine how technology is enabling a new resource frontier: space mining. Our planet contains finite resources, yet our technological civilization requires an ever-increasing supply of metals, minerals, and other materials. Meanwhile, orbiting above us are asteroids containing quintillions of dollars worth of resources: platinum, gold, rare earth elements, water, and more, in concentrations far higher than Earth's richest mines. From near-Earth asteroids to the lunar surface to the moons of Mars, the solar system contains virtually limitless resources that could transform our economy and enable sustainable development both on Earth and in space. The convergence of advanced robotics, artificial intelligence, quantum computing, and new space launch capabilities is making this once-distant dream an emerging reality. In this episode, we'll explore the resources available in space, examine the technologies being developed to identify and extract these resources, consider the economics and legal frameworks of space mining, and contemplate how this new resource frontier could reshape humanity's future, both on and off our home planet. To understand the potential of space mining, we first need to appreciate the extraordinary abundance of resources in our cosmic neighborhood. Asteroids are perhaps the most promising initial targets. These space rocks come in several types, each with different resource profiles. C-type, carbonaceous asteroids contain water, organic compounds, and carbon, crucial for life support and fuel production. S-type, silicaceous asteroids contain silicon, iron, magnesium, and smaller amounts of precious metals. The rarer M-type, metallic asteroids are the true treasure troves, containing up to 10 times the concentration of precious metals found in Earth's richest mines. The scale of these resources is staggering. 16 Psyche, a 140-mile-wide M-type asteroid in the main belt, contains enough nickel, iron, gold, and platinum to potentially be worth $10 quintillion, more than the entire current global economy. Even modest-sized, near-Earth asteroids can contain billions or trillions of dollars worth of resources. The Moon offers different but equally valuable resources. Its regolith, surface material, contains titanium, aluminum, and iron. The lunar poles harbor water ice in permanently shadowed craters, a crucial resource for life support and fuel production. Perhaps most intriguingly, the Moon contains significant amounts of helium-3, a potential fuel for future fusion reactors that is extremely rare on Earth. Mars and its moons, Phobos and Deimos, represent another potential mining frontier. The Martian surface contains abundant iron, aluminum, and titanium, while its atmosphere can be processed to produce oxygen and fuel. Phobos and Deimos may be captured asteroids, potentially rich in water and metals. Dr. Angel Abud Madrid, director of the Center for Space Resources at the Colorado School of Mines, explains, "What makes space resources so valuable isn't just their abundance, but their location. It costs thousands of dollars to launch each kilogram from Earth into orbit. Resources already in space have an inherent advantage. They're already halfway to anywhere in the solar system, energetically speaking." This tyranny of the rocket equation means that utilizing space resources could dramatically reduce the cost of space exploration and development. Water mined from asteroids or the lunar poles could be split into hydrogen and oxygen for rocket fuel, creating refueling depots in space. Metals could be used for construction in orbit, avoiding the need to launch structural materials from Earth's deep gravity well. The concept of using space resources isn't new. It dates back to the early days of the space program. But recent technological advances and the emergence of commercial space companies has transformed it from theoretical concept to emerging industry. Turning the vision of space mining into reality requires solving numerous technical challenges across the entire mining value chain: prospecting, extraction, processing, and transportation. The first step is identifying promising targets. Earth-based telescopes and space observatories like the James Webb Space Telescope can analyze the spectral signatures of asteroids to determine their composition. Dedicated prospecting missions like NASA's Psyche mission, launching in 2023, will provide more detailed information about specific high-value targets. Artificial intelligence plays a crucial role in this prospecting phase. Machine learning algorithms can analyze vast datasets from telescopes and spacecraft to identify the most promising mining candidates based on composition, orbit, rotation rate, and other factors. These AI systems can recognize patterns and correlations that human analysts might miss. Quantum computing enhances this prospecting capability. Quantum algorithms can simulate the internal structure and composition of asteroids based on limited observational data, providing insights that classical computers cannot. This helps mining companies target their efforts more precisely, reducing risk and increasing efficiency. Once a promising target is identified, the next challenge is extraction. Several approaches are being developed. 1. Surface mining. Robots collect material from the asteroid surface using scoops, drills, or other mechanical means. 2. Magnetic separation. For metallic asteroids, magnetic systems can collect metal particles. 3. Thermal mining. Concentrated sunlight heats volatile materials like water ice, causing them to sublimate for collection. 4. Bag and tag. For smaller asteroids, enclosing the entire body in a bag and processing it in a controlled environment. These operations must be largely autonomous due to communication delays. AI systems enable robots to adapt to unexpected conditions, make real-time decisions, and coordinate complex operations without human intervention. Processing the extracted materials presents another challenge. Traditional mining on Earth relies on water, chemicals, and substantial energy, all limited resources in space. Novel approaches being developed include 1. Molten regolith electrolysis, using electricity to separate metals from oxygen in lunar or asteroid material. 2. Vapor phase pyrolysis, heating material until it vaporizes, then collecting specific elements as they condense at different temperatures. 3. Biological processing, using engineered microorganisms to extract specific elements. Dr. Joe Searle, founder of TransAstra Corporation, explains their approach. Our optical mining technology uses concentrated sunlight to excavate asteroids. It heats the surface, causing thermal stress fractures, while simultaneously driving off volatile compounds like water that can be captured. It's an elegant solution that requires minimal moving parts and uses the abundant solar energy available in space. Finally, the extracted resources must be transported to where they're needed. Options include 1. Solar electric propulsion, using electricity from solar panels to power ion thrusters. 2. Tethers and mass drivers, using momentum exchange to throw processed materials to their destination. 3. Solar sails, using the pressure of sunlight for propulsion. 4. In-situ fuel production, using extracted water to produce hydrogen and oxygen rocket fuel. Many of these technologies are moving from concept to reality. NASA's OSIRIS-REx mission successfully collected samples from asteroid Bennu in 2020. The Japanese Hayabusa 2 mission returned samples from asteroid Ryugu in the same year. While these were scientific missions, they demonstrated key capabilities needed for commercial space mining. The technical feasibility of space mining is increasingly clear. But what about the economics? Is there a viable business case for extracting resources from space? The initial business case focuses not on returning resources to Earth, but on utilizing them in space. The cost of launching materials from Earth, currently $1,000 to $10,000 per kilogram, creates an opportunity for in-space resource utilization. Water is particularly valuable, as it can be used for life support, radiation shielding, and rocket propellant when split into hydrogen and oxygen. A space-based fuel infrastructure could dramatically reduce the cost of missions beyond low Earth orbit. Satellites could be refueled, extending their operational lives. Missions to the Moon, Mars, and beyond could refuel in orbit, allowing smaller, more efficient launch vehicles. Morgan Stanley estimates that the global space economy could grow from around $350 billion today to over $1 trillion by 2040, with space mining playing an increasingly important role in that expansion. Several companies are pursuing this opportunity. Asteroid mining pioneers like Planetary Resources and Deep Space Industries were acquired by larger aerospace firms after facing funding challenges. New entrants include 1. TransAstra, developing optical mining technology for asteroid resource extraction. 2. Carmen Plus, focusing on lunar resource utilization. 3. Astroforge, planning to launch its first prospecting mission in 2023. 4. Bradford Space, developing water extraction technology for asteroids and the Moon. Space agencies are supporting these efforts through partnerships and contracts. NASA's CLPS, Commercial Lunar Payload Services program, is sending commercial landers to the Moon, some carrying resource utilization experiments. The European Space Agency's Space Resources Strategy emphasizes public-private partnerships to develop necessary technologies. Chris Lewicki, former CEO of Planetary Resources, offers perspective. The first trillionaire will be made in space resources, but the path there isn't straightforward. The initial value isn't in platinum or gold. It's in providing services in space for space. Water for fuel, materials for construction, resources that enable a sustainable presence in space. Most experts envision a phased approach to space mining. Phase 1, 2020s, prospecting and technology demonstration missions. Phase 2, 2030s, initial commercial operations focused on water extraction for in-space use. Phase 3, 2040s, larger-scale operations including metals for in-space manufacturing. Phase 4, 2050s plus, potential return of high-value materials to Earth if economically viable. The long-term economic impact could be transformative. UBS estimates that space mining could eventually become a $100 billion annual market. More importantly, it could enable a broader space economy worth trillions by providing the resources needed for sustainable space development. As technical and economic barriers to space mining fall, legal and ethical questions come to the forefront. Who owns space resources? How should they be regulated? How can we ensure equitable access and environmental protection? The legal framework for space activities begins with the 1967 Outer Space Treaty, which establishes that space is the province of all mankind and that no nation can claim sovereignty over celestial bodies. However, the treaty doesn't explicitly address resource extraction. Several countries have enacted national legislation to provide legal certainty for their companies. The United States passed the Commercial Space Launch Competitiveness Act in 2015, recognizing the right of U.S. citizens to own resources they extract from asteroids. Luxembourg, the United Arab Emirates, and Japan have passed similar laws. The Artemis Accords, initiated by the United States and signed by over a dozen countries, establishes principles for cooperation in space exploration and resource utilization. They affirm that resource extraction is compatible with the Outer Space Treaty and commit signatories to transparent operations and sharing of scientific data. Not all countries agree with this interpretation. Some argue that a new international treaty is needed to ensure equitable access to space resources, particularly for developing nations that don't yet have space capabilities. The UN Committee on the Peaceful Uses of Outer Space continues to discuss these issues. Dr. Tanya Masson-Swan, former president of the International Institute of Space Law, explains, "We're in a period of legal evolution. The Outer Space Treaty provides basic principles, but it was written before commercial space activities were significant. We need to develop more detailed frameworks that balance encouraging investment with ensuring benefits are shared broadly and preventing harmful practices." Environmental considerations also arise. While space lacks ecosystems that could be damaged by mining, operations could create orbital debris that threatens other spacecraft. Mining could also alter celestial bodies that have scientific or cultural value. Some advocate for establishing protected areas on celestial bodies, similar to national parks or marine reserves on Earth. Proposals for sustainable space mining include 1. Space sustainability ratings that evaluate missions based on their environmental impact. 2. Requirements to preserve scientific data about celestial bodies before altering them. 3. Obligations to remove or repurpose equipment after mining operations conclude. 4. Benefit-sharing mechanisms to ensure space resources contribute to human development broadly. The legal framework will likely continue to evolve through a combination of national legislation, bilateral agreements, multilateral treaties, and industry self-regulation. This evolution will shape not just who can mine in space, but how those operations are conducted and who benefits from them. Beyond the immediate business case for space mining lies a more expansive vision, a solar system economy where resources from multiple celestial bodies support human activities both in space and on Earth. In this future, materials mined from asteroids and the Moon could supply manufacturing facilities in Earth orbit. These facilities could produce satellites, spacecraft components, and eventually entire space habitats, taking advantage of unique space conditions like microgravity and abundant solar energy. Space-based solar power, massive solar arrays in orbit beaming energy to Earth via microwaves, could provide clean, continuous energy. Building these enormous structures would be prohibitively expensive if all materials had to be launched from Earth, but becomes feasible using space resources. Larger-scale space habitats like the O'Neill cylinders envisioned by physicist Gerard O'Neill could eventually house thousands or even millions of people. These would require vast amounts of material, primarily from the Moon and asteroids, for radiation shielding and structural elements. On Mars, in-situ resource utilization would be essential for sustainable settlement. Extracting water, oxygen, and building materials from Martian regolith and atmosphere would dramatically reduce the mass that needs to be transported from Earth. This space resource economy could benefit Earth environmentally by moving extractive industries off-planet. Rather than mining increasingly marginal ore deposits on Earth with associated environmental impacts, we could access the abundant high-concentration resources of space. Dr. Phil Metzger, a planetary scientist and space mining expert, explains, "The vision isn't just about mining asteroids, it's about creating a sustainable industrial presence beyond Earth. Once we can use the resources of space to build in space, we unlock exponential growth potential. Each facility we build can help build more facilities, creating a positive feedback loop of development." Economically, this expanded space economy could eventually dwarf Earth's current economy. Jeff Bezos, founder of Blue Origin, has suggested that the solar system could support 1 trillion humans, with economic activity thousands of times greater than today's global economy. This grand vision would unfold over generations. 2020s to 2030s, initial prospecting and demonstration of key technologies. 2030s to 2040s, first commercial operations focused on water and fuel. 2040s to 2060s, expansion to metals and in-space manufacturing. 2060s to 2100s, large-scale space development including habitats and solar power. 2100s and beyond, solar system-wide economy supporting Earth and space settlements. Significant challenges remain, from technical hurdles to economic uncertainties to governance questions. The timeline could accelerate with breakthroughs in key technologies like fully reusable launch vehicles, advanced robotics, and space manufacturing. It could also be delayed by setbacks, economic downturns, or international conflicts. Philosophically, space mining represents a potential solution to the tension between growth and sustainability. Earth's resources are finite, but the resources of the solar system are vast enough to support human civilization for millions of years. By accessing these resources, humanity could continue to develop and expand while preserving Earth's natural environment. Space mining represents one of the most significant resource frontiers in human history, comparable to the discovery of the Americas or the development of offshore oil drilling, but potentially far more consequential for our long-term future. The convergence of advanced robotics, artificial intelligence, quantum computing, and new launch capabilities is making this once-distant dream an emerging reality. From prospecting missions launching in the next few years to initial commercial operations planned for the 2030s, we're witnessing the birth of a new industry that could transform our relationship with space and the Earth itself. The challenges remain substantial: technical, economic, legal, and ethical, but the potential rewards are equally substantial. Resources to support sustainable development both on and off Earth, new industries and economic opportunities, and perhaps most importantly, a path to becoming a true spacefaring civilization with access to the vast resources of our solar system. In our final episode of this series, we'll explore the ultimate technological convergence, the technological singularity, where AI, quantum computing, and other advanced technologies may create a future that's difficult to predict or even imagine. Until then, this has been Click Future, where your future is a click away. If you found this exploration of space mining fascinating, please like this video and subscribe to Click Future for more insights at the cutting edge of technology. Share your thoughts in the comments below. Do you think we'll see commercial space mining in your lifetime? And how might access to space resources change our future on Earth and beyond?